So we sometimes nickname that one right-hand rule number two, but what does this formula really say? Because after a while, looking at these formulas, they start to say nothing. They just are a bunch of letters, and you can calculate them, but all it is trying to quantify how strong a magnetic field there is around a current carrying wire. So it's about, right, electromagnetism. Now, the second formula is actually older. We learned that one first. So we could refer to that one as right-hand rule number one. Just if you're like talking with me or talking with classmates as you solve things. It's maybe in the past we didn't use the absolute value, but it's Q times V times B times sine of theta. It's the two vectors crossing. So this one has nothing to do with measuring magnetic fields. It has to do with, of course, force that a moving charge experiences when it crosses a B field. Remember, we call this a cross vector product, and that's why you have to introduce sine. Okay? Now, I want to actually briefly show you that F equals ILB is another version of the exact same formula. And apparently, it's used for, instead of bare charges moving through like outer space or through a vacuum, it's when a wire is carrying current and you put that wire into a magnetic field. So a wire carrying current should be the same as moving charges because that's what electricity is. And it seems like it should be the same principle. So if you think about what these letters stand for, and I have to explain one or two of them, they look like they're the same, but they're not. That's current multiplied by the length of the wire and multiplied by the strength of the B field. And what we get there is the same quantity. How much current multiplied by the length of the wire times the B field. And you're like, how can it just be the same thing? Well, remember what's inside current. It's usually an ampere, but that's really a coulomb per second. That's what an ampere is made of. Length is meters, and the B field is, of course, Teslas. Sorry, I wrote over top of the word force. And what you notice is that that is the exact same units as the formula above it. C would be the unit for Q. Velocity would be meters per second. And I see that. It's just, they're just not together. They're separated. And then lastly, Teslas. So I don't want to spend too much more time introducing that formula, but it is a cousin formula, so to speak, and it's for wires that go through magnetic fields. A really simple formula. So that's new today, but it's kind of basic. We haven't tried a practice problem with it yet. Okay, what's not so easy is that before you can answer all 8 questions, actually we're skipping number 1, is there's a new topic, and it's the last idea of this unit on magnetism.
Hello?
And I've got a couple of. Hello, everyone. Tim, are you there?
Did you just notice that, like, right now? Dude,
what did we notice, Tim?
Wait one second.
I think Tim might not have been muted. I just muted him. He might be working on something. Okay. So hopefully he's okay. So is this last idea. It's called magnetic induction. And magnetic induction is kind of like related, but different than electric induction. In electricity or charges, induction was a non-contact way of charging. In the physics of magnets, electromagnetic induction is a way of creating an electric field using magnetism. Well, I remember an electric field, right, can create, right, a potential difference or voltage. And if you do that in a conductor, electric fields When you're close to one side of the terminal versus the other, the positive or negative, charges have different potential energies and different voltages. So essentially what we're saying in this, and we're going to get into the nitty gritty, is that if you change a magnetic field in the presence of a conductor, near a conductor, current and voltage are created. So some people have figured out that essentially what this is the a final and really big, don't worry about this yet, a really big connection between electricity and magnetism. Magnetism, when it changes, when you make it stronger or weaker near a conductor, will make electricity. But we know that moving electric charges make magnetism. And some people refer to this as something called a dynamo. Magnetism changing can give way to current, and electric current creates magnetic fields. And a dynamo is this idea that two ideas reinforce each other. So, first, before we can quantify induction, the induced current, we have to find out about this guy, something called magnetic flux. And it sounds like it's right out of science fiction. And to flux means to go through something in like a spatial way. So, I'm trying to think. I was trying to come up with props, and I don't have a perfect prop for this situation. Okay. But I'm going to take a paperclip and I'm going to turn it into some kind of like, you know, polygon. It's kind of triangular. It's not quite circular. If I bent it enough, I could make it into any shape I suppose I want. Let me flatten it out. Okay. And this loop, right, could be a cross section of a piece of steel, of metal. And when you put a magnetic field through it, now, what kind of magnetic fields could this be? Well, I happen to have right here some really strong magnets. They're pretty cool, but they're also a little dangerous. Got to keep them away from hard drives. Yeah, you can see how strong this is. Now, this is spherical. I wish it was a north-south magnet, but I didn't bring any of those home, like a bar magnet. But when the magnetic field goes through the loop, right, and you can't see this, but it's referred to, it's invisible, but it's referred to as flux. So this magnet through this area, and it's like basically just a bent paper clip. In the model on the paper, it's a random shape. It kind of looks like a blob. And what you're seeing here is the magnetic field is going through this area. And depending on how much magnetic field goes through that area, it determines how much flux. And the symbol for flux is a phi. So if you hold a magnet close to this wire and it's stationary, you have a certain amount of flux. Okay. And again, this wire is actually attracted. I wish I had copper wire. I don't have any copper paper clips. Okay. But then if I move the magnet farther away, the magnetic field is definitely weaker. I can no longer feel the paperclip pulled toward it. And if I get closer, the magnetic field is going to get more intense, farther away or closer. So depending on how the magnet is positioned, it will change the amount of flux. Because if I change how strong the B field is, I'm changing my flux. I can also do something weird where I change the area of the cross section. Now, you can see the paper clip is kind of like a triangle shape, and it's right now I'm holding it up vertical. So the area of that triangle is could be calculated if you knew its base and its height and things like that. And I can change how the magnetic field interacts by also twisting the coil, because the magnetic field is still pointing in the same way. It's no longer going through the conductor. It's going kind of over the top of it and below it. Let me show you what I mean by that. So this has got a ton of flux if I hold this triangle shape, and this has very little flux because the magnetic field is no longer going through the loop. It's going maybe parallel to the loop. Okay, so what's the point of flux? Well, flux happens all the time. Magnetic fields exist, and there's metal conductors. Well, if there is a change in the flux, that's what that symbol stands for. Oops, change has an E in it. If you change the amount of magnetic flux per second, right, per time, you get an EMF. And an EMF is a voltage. It's another name for a voltage, but it's used when there is no chemical reaction, but there's a magnetic field change. So Faraday's law, right, is referred to as the law that describes, right, how you get a voltage from a moving magnet. Now, and you're like, this is made up. This is another situation where you've seen this hundreds of times. You just didn't know you were seeing it. Okay, so this is a flashlight. Does the flashlight have a good battery in it? It's pretty good, but it's not too bright. Okay, sorry for shining that right in the camera, but sure, it's not too bright. Now, it's almost clear, but do you notice that when I slide it, something is moving? It's kind of like a frosted plastic. What that is a magnetic slug, and it's got a north and a south, and it's got rubber bumpers so that the magnet doesn't bang into the end. And this is a massive coil of wire. So every time the magnet moves through, it's getting stronger, and then it goes through it and gets weaker on the other side. And then it goes through the other way. And every time I do that, and if you shake it back and forth, shake weight style, you actually can store some energy in this battery. So this is a flashlight that is essentially rechargeable by just kind of jostling the magnet back and forth. And you're like, well, how long does that last? Well, I took this out of the cabinet at school. Like, I don't remember the last time I was in school. And this was already charged. So it must be holding its charge. And I haven't even added any more, oops, come on, focus, induction to it. So I haven't even charged it up except for what you've seen here. So this is a great example of electromagnetic induction. Okay. So um, all we need to be able to do with this, and you're not going to be accountable for the math so much of what's called Lenz's law, but here you see, right, Faraday's law, and then you rearrange the formula, and you ultimately get, right, the EMF, the voltage, ends up inducing, right, a charge based on how strong is the B field, how long is the wire, and how fast are the charges going through it. I want to spend just a little bit more time, just a minute more, showing you a couple of other amazing applications of this. So let me change what I'm sharing. Sorry, you're looking at my mouse. And this is a little underwhelming when you're not seeing it in person. I'm going to have to agree. There's so many cool things we can do together. And the first one is, in case there's a couple of guitarists in the room, or people, you know, did I share it correctly? No, I think I did. Yeah. So here's a guitar pickup. And a guitar pickup is that those metal bars that are underneath an electric guitar. I guess it could be, yeah, they have to have metal strings. And when you plug it into the amplifier, each one of the pickups is actually a small magnet and wrapped in a coil, and that goes off to the amplifier. And when you pluck the string, it causes a change in the magnetic field. Each of the wires in an electric guitar becomes a magnet, and it creates its own magnetic field. Why does that happen? Because the pickups are electromagnets themselves. But then when the wire vibrates, because you pluck it, it actually causes a current to jiggle back and forth or to alternate back and forth. And when that is sent to the amplifier, do you notice that the arrows that are wiggling back and forth seem to be going at the exact same frequency as the wire? And for those of you who are musicians, you know that when you're, whether it's your vocal cords, a piano, or other instruments, when there is a vibrating source that, such as a wire, and we would like to hear its frequency, because that's what music is, the frequency of the wire becomes the frequency that goes into the amplifier, and you get much louder music because you can kind of pick it up. The second cool demonstration of electromagnetic induction is actually the other end of the music connection. It's actually in the speaker system. So there's the pickup on the guitar, but then the wires carry that over to the speakers, or the amplifiers, as you may call them. And because the current changes direction, now this is a very complicated demo, and I'm going to be putting this on our assignment page. What it shows is that as the electric current switches back and forth in this huge electromagnet, it induces a movement in this coil because this is a permanent magnet. And lo and behold, this is called a voice coil. Not voice as in you're singing, but it's the backside of a speaker, and it's what pushes the air at you, and that's what makes sound. So it's an electromagnet that is changing its current near a permanent magnet, which is inducing a current. It's kind of a little more than we can do in 25 minutes, but we'll see this in some videos I post. And just to be clear, and I know some people are already scooting out, so I'll keep this real brief. Your assignment is page 10. And again, this will be posted, of course. Stop sharing that page. And let me show you. It's pretty easy. Sorry, there we go. Camera. Okay. This page is now doable. Let me zoom all the way out. This is page 10 and page 11. Most of them are calculations, but a couple of them are short answer. So you can handwrite these out, or you can turn these in. So